Okay, so what we're going to do is we're going to start to talk about vectors today. And so we are beginning on section 9.3. This is 9.3 day 1. And this is going to be vectors. And this is going to be our geometric approach. There are two different ways to approach vectors. One is the geometric approach. The other one is the algebraic approach. Section 9.3 is the geometric approach. We'll do the algebraic approach in section 9.4. So the first thing that you need to do is understand what a vector is. And typically what we're going to do with vectors, or the way we're going to represent them, is going to be something along the lines of this. It looks like a ray from geometry. But there is a distinct difference between a ray and a vector. A ray in geometry means that you have an endpoint, and then you have it moving in one direction, and it continues in that direction forever, so off to infinity. That's for a ray. Vectors do not work that way. There are 2 points on a vector. The first one is known as the initial point. And the other one at the tip of the arrow is known as the terminal point. Meaning that it ends there. So the arrow on vectors does not indicate that it goes on forever. It indicates which direction the vector is pointing. And so what we use vectors for is we typically use vectors to represent things like force or velocity, things that have 2 components to them. And so vectors have 2 components. One component is the magnitude. In other words, the size, the strength, the speed, etc. It's the numerical part of the vector. And the longer the vector, the greater the strength of the force or the speed associated with the velocity, etc. And so the length of vectors is very, very important. So that's our magnitude. So if you have a vector that's representing a force of 2 newtons, it might look like that, but a vector with a force of 4 newtons would be twice as long. So this might be a force of 2 newtons. This may be a force of 4 newtons. Okay, so the length is very, very important. The other thing that's important besides magnitude, length, is direction. Now there are a number of different ways that we can measure direction for vectors. What we are typically going to do to measure direction is we are going to measure direction in standard position, meaning as an angle measured from the positive x direction, counterclockwise. Okay? So just like we did with the unit circle, we start with 0 degrees pointing in the positive x direction, and we increase as we go this way. So for example, this may be a 40-degree direction for this vector if theta is 40 degrees. Okay? So every vector has a magnitude represented by the length that it's drawn with, and it has a direction. Now there are other ways to measure direction. You can also measure direction using the cardinal points of a compass, north, south, east, west. And you can go north of due west or south of due east and things like that. We're going to typically, unless it's otherwise stated, measure them in standard position. If you measure an angle, a direction angle for a vector in standard position, you do not need to give any north, south, east, west directions to go with it. It is understood that you're talking about standard position unless you specify otherwise, or unless they specify otherwise. Okay. So the next thing that's important to understand about vectors is that these are the only 2 things that make a vector unique. The magnitude and the direction. Notice I did not say anything about the position of it. So what that means is that vectors are portable. So if I have a vector, I can take that vector, and as long as I don't change the length of that vector or the direction of that vector, I can move that vector anywhere I want to, and it is still the same vector. As long as the magnitude and direction stay the same, it's the same vector. It doesn't matter where I put it. Now, as soon as I do this, now it's not the same vector. Because now we've changed, not its magnitude is still the same, but its direction has changed. It's now a new vector. Okay? Now, the way that we name vectors, there are two different ways we can name vectors. One is by the initial and the terminal point. So let's say this is P and this is Q. We can call this vector PQ. The problem is this is typically the way that books will show this. But that is the symbol for array. We don't want to use the same symbol, in my opinion, for two different kinds of objects. This would indicate array in geometry that starts at P and moves past Q forever. So when I'm writing things, it's fine with me if you use the book's notation, although I'm not a big fan of it. My preference would be for you to do it the way that I learned it 1,000 years ago, and that is that you distinguish a vector from an array by using this symbol. So you only have half of the arrowhead. And so when you see this half an arrowhead, and this is still a symbol that's oftentimes used today, this indicates that it's a vector that starts at P and moves towards Q and then stops. So now we know that it's a vector and not array. Okay. So what we're going to do now is we're going to talk about putting vectors. We're going to talk about how to find magnitude and direction. Excuse me. Let's do that first. So let's say we have a vector that looks something like this. And let's say, actually, I'll tell you what. Let's do it this way. Let's put it on a graph so we can talk about its components a little more specifically. Let's say I have a vector that starts here and goes to here. So this vector is starting here at negative 1, 1, and it's going to here, which is at 3, 3. Call this P, we'll call this Q. So this is vector PQ, with P having coordinates negative 1, 1, and Q having coordinates 3, 3. When we want to talk about the magnitude of this vector, what we're going to do is we're going to take this vector and we're going to make it the hypotenuse of a right triangle. So I'm going to drop straight down vertically and go over horizontally. Notice that this vertical piece is 2 units, and notice that this horizontal piece is 1, 2, 3, 4, 5 units. And so if we want to, and this is a right triangle, so if we want to find the length of the vector, that is the length of the hypotenuse, we can use the Pythagorean Theorem. So 2 squared plus 5 squared equals c squared. So that's 4 plus 25. So 29 equals c squared, which makes c equal to the square root of 29. Or if they ask you for a decimal, you could obviously punch that into your calculator and get it as a decimal, typically rounded to 1 decimal place. We'll leave it as the square root of 29, though, for here. There is our magnitude. And the way we would indicate the magnitude is we take the name of our vector, PQ, with the symbol, and we put absolute values around it. Okay, by putting the absolute values around the name of the vector, that means the magnitude of vector PQ, and that ends up being the square root of 29 units, newtons or miles per second or whatever it happens to be. Now for the direction, it's going to be this angle right here, theta, that we're interested in, measured from the positive x direction. If the vector was pointing this way, then theta would go from the positive x direction over to where the vector is. And so the way that we're going to do that, because we have a right triangle, is we can use SOHCAHTOA, and it turns out that tangent of our direction angle, theta, is equal to opposite over adjacent. So therefore, theta is inverse tangent of 2/5. We're going to punch this into our calculator. So I'll make sure that I am set to degrees, which I am. And so I'm going to do inverse tangent of parentheses 2 divided by 5. Gives me an angle of about 21.8 degrees. Let me just double check that. That was, yes, 21.8 degrees. That is our direction. So here is your magnitude. Here is your direction. So that's magnitude and direction using the Pythagorean Theorem and using SOHCAHTOA. Okay, what we're going to do now is we're going to take a look at adding vectors together. Before I do that, I want to show you that there is another way to label vectors, and that is that we can also label vectors as a single letter with the vector symbol above it. So if I want, I can call this vector v, and I just use the vector symbol above it. So if I want, this could be called vector v going from p to q, and so we would say that the magnitude of vector v is equal to the square root of 29. So that's an alternative way to do it. Typically what your book will do is they will use a boldface type for vectors with single letters. The problem is we can't really do that when we're writing by hand because we can't really tell the difference between an intentional boldface and an accidental boldface or just a heavy hand. So that's why we use the vector symbol. Okay. What I want to do now is I want to take some points. Point O is going to have coordinates 0, 0. Point P is going to have coordinates 1, 3. Point Q is going to have coordinates -2, 4. And point R is going to have coordinates 3, 5. And what we're going to do is we're going to do things like vector PQ plus vector QS. And so I'm going to take my graph, and again, this is the geometric approach, so we're using Cartesian coordinates here. We have P, which is at 1, 3. We have Q, which is at -2, 4. And, oh, I'm sorry, guys, this should have been QR, excuse me. Sorry about that. So PQ plus QR, R is at 3, 5. So what we have is we have a vector going from P to Q. Then we have a vector going from Q to R, and we want to add those together. These vectors right here happen to be in what we call tip-to-tail arrangement, where you have the first vector with its tail at P and its tip at Q. The tip is the tip of the arrowhead. And then the tip of the first vector attaches to the tail of the second vector, which then goes from Q to R. And when we add vectors together, this is one method for doing it, called tip-to-tail method, where again, you take the tip of the first one, attach it to the tail of the second one, and then if you have more than two, you can take the tip of the second one, attach it to the tail of the third one, etc. Your resultant vector, which is what we call the vector that's a result of any kind of manipulation of these vectors, is going to go from the starting point to the final ending point. So imagine that you're walking on a path, and you start at point P, and you walk from P to Q. Then at Q, you change directions, and you walk from Q to R. Well, the net change in your position would be as if you had just walked straight from P to R. That is our resultant, and I'm going to call that vector R for resultant. I'll use a lowercase r to not confuse it with the point R, and I'll put the vector above it. So what we are looking for then is we are looking for R, the resultant. We want to know what its magnitude and direction is. And so to find its magnitude and direction, again, what we're going to do is we're going to make it into a right triangle with the right angle down here. This is 1, 2 units. This is 1, 2 units. And so we know that 2 squared plus 2 squared equals the magnitude of R squared. That's 4 plus 4 is 8, so we get the magnitude of r squared equals 8. So the magnitude of r is going to be the square root of 8, which is 2 square root of 2. Magnitudes are lengths, so they have to be positive. And so there's our magnitude of r. Now, if we want to find our directional angle theta right here, then again, we're going to use tangent of theta equals opposite over adjacent. So tangent, sorry about that. Let me restart my tablet here real quick. Bear with me just a moment. There we go. Let's see if that works better. Tangent of theta is equal to opposite over adjacent, which is 1. So theta equals inverse tangent of 1. You can punch that into your calculator, but we know tangent is 1 at 45 degrees. We can also see that this is a 45, 45, 90 right triangle right here. So our direction is 45 degrees, and our magnitude is 2 square root of 2 units, newtons, whatever. Again, we can string as many vectors as we want together, tip to tail. That's not a problem. Now, what we're going to do next is we're going to look at a slightly different problem using these same points. And so now what we're going to do is we're going to do, so that was the first example. The second example is going to be OP plus RQ. OP plus RQ. So O is here. P is at 1, 3. So here's vector OP. Put that in green. We have R, which is at 3, 5. Q, which is at negative 2, 4. So here is RQ, going from here to here. So notice that these are not in tip-to-tail arrangement, but remember I said that vectors are portable. So what we can do is we can move vector RQ so that R corresponds with P. And so what we do on the computer, it's very easy because I can just take this and I can drag it over there, and I'm done. Obviously, you can't do that on your paper. So how do you do it? What you do is you notice that from R to Q, you basically look at the slope. Notice it has a rise of negative 1 and a run of 1, 2, 3, 4, negative 5. So it goes down 1 and to the left 5. So from P, we go down 1 and to the left 1, 2, 3, 4, 5. And notice when I drag this back down, sorry, did I go too far? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Sorry, I put that point in the wrong place. That point should have been right there. Sorry about that. Okay. So we go down 1 into the left 5, and then we can draw our vector. And now we have tip-to-tail arrangement. Okay. So there is another method for doing this, and that is what's called the parallelogram method, where what you can now do is you can now make a parallelogram out of this by going down 3 to the left 1, 1, 2, 3 to the left 1, and you notice that this becomes a parallelogram, and so the resultant ends up being the diagonal going this way. I don't see any real benefit to doing the parallelogram method. Tip to tail is a shorter method because you're going to have to essentially do tip to tail when you draw the parallelogram anyway. So I would just stick with tip to tail. And so our resultant, let me change it to red, our resultant is going to go from where we started to where we ended. There is our resultant. And so what we're going to do now is we're just going to find the magnitude. I'm not going to worry about the direction right now, but just to find the magnitude of this, we make it into a right triangle. Notice we have 2 units here. Notice we have 1, 2, 3, 4 units here. I'll call this vector r for resultant. And so the magnitude of r squared is equal to a squared plus b squared. 16 plus 4 is 20. So the magnitude of r is equal to the square root of 20 equals 2 square root of 5. Now we could find the direction on this also, but these kind of problems in the book I believe are only going to ask you for magnitude. They're not going to ask you for direction, so I'm not going to worry about that. What you would do, however, to find the direction is you would do tangent and find this angle here, but remember that we need to measure this starting from the positive x-axis. We really care about this angle. So whatever answer you got from doing inverse tangent of 2 over 4, what you would do is you would do 180 minus that value, and that would give you this angle out here. But again, I don't believe they're going to ask you for that on the homework. Okay, there's one other example I want to do for you, because it's related to what we talked about, and that is we have two forces, F and G, that act on an object. It turns out that F is vertically upward, G is horizontally to the right. And so what that means is we have a vector that acts upward, that's F. Sorry, I would like to keep red for the resultants. So vertically upward, and F, they're going to tell us, is 3 newtons. So this is 3 newtons. G is going to act horizontally to the right, and it's going to be 7. So it's going to be a little bit more than twice as long. So there are 2 vectors. This is F, this is G. What we want to do, and notice these are at a right angle to each other. What we want to do is we want to find the resultant. So what you can do is you can do tip to tail. You can take this guy and you can move it over here and then draw your resultant in. Or you could do it using the parallelogram method that we talked about just a moment ago. Make this into a parallelogram, which because of the right angle happens to actually be a rectangle. And so our resultant, again, is going to be this magnitude. I'm sorry, this diagonal. Excuse me. There we go. That's the resultant. The nice thing is, because this is a parallelogram, if this is 3, this is also 3. This is 90, this is 90. So again, we have our right triangle. We can find our magnitude and our direction. So the magnitude of r squared, that's our c squared, equals a squared plus b squared. That's 9 plus 49 is 58. And so the magnitude of r is equal to the square root of 58. That doesn't simplify, but if they wanted it on the calculator, we could do the square root of 58. Let's say they asked us for it. That would be about 7.6 newtons. We know that tangent of theta is opposite over adjacent, so theta equals inverse tangent 3 over 7. Go to the calculator. Second function tangent, parentheses, 3 divided by 7 is going to give us an angle of approximately 23.2 degrees. So now we know the resultant force. So imagine that you have an object sitting here. And you have one force that's pushing it this way, and you have another force that's pushing it this way at these strengths. The red arrow, the red vector, tells you how far and in what direction that object is going to move when you apply both of those forces simultaneously. That's the idea. So it's going to move 7.6 with a force of 7.6 newtons at an angle of 23.2 degrees counterclockwise from the positive x-axis. Okay, so that's going to cover what we have today. We'll cover the rest of the section in the next video.